Okay. So yesterday we did like the different, questions related to intensity. And today we are going to, I think it would be best if we start with Doppler's effect. So let's do that. Okay. So let's write the definition first. The Doppler effect is defined as the apparent change in frequency observed by a stationary observer when the source of wave is moving relative to the observer. In this, there are two keywords like apparent change and moving relative to the observer. So you please write this down and then I'll explain to you what this means. Okay.
And the source of wave
is moving, sorry, my bad, moving relative to the observer. Alright? Now, so suppose there is a source. There's one person right here who's the observer 1, and there's one person at the same distance from the source as observer 2. We're on the other side, okay? So the source is producing sound waves or any kind of wave, doesn't really matter. And basically these waves have wave fronts just like this. So they have the same lambda on both sides and they can observe the same sound because this source is currently stationary like this. Is it clear, everyone? Now, yeah. What I'm saying is that the source is in the center. It could be anything, an ambulance, a light source or something. So it's basically the waves are spreading in all directions, right?
Yes.
So observer 1 and observer 2, which are like standing on both sides at the same distance right now, they can actually experience the same wavelength of whatever that wave is. Is it clear?
Okay.
Now, when this source is right here starts to move So actually what happens is that when it produces a wave, the wave travels and also the source travels forward. So there's all the time a larger like gap that is developed behind it. Do you understand this? So this person who's the observer one experiences higher wavelengths than the observer 2 who's right in front of him, front of the source. Is it clear? This is basically the velocity of source. So what I'm saying is it's producing the sound, but while it's producing sound, it's also moving in a certain direction. So it produces the next sound. In front of it, the wavelength decreases, and at the back of it, the wavelength increases. So this is called the Doppler's effect. All right. So with respect to the observer, we can actually say, I'm going to show you a few of the like real things you'll understand. But first, let's write the conditions when sources, when the source is moving away, what happens then? And then we are also going to write when the source is moving towards an observer. So what happens then? In a case when source is moving away, observed frequency is lower than actual frequency, because if you look at him, the observer one is experiencing this, that source is moving away. So observed wavelength is higher than actual wavelength. So obviously, if you look at the formula, v is equal to f lambda, speed is the same. So if the wavelength apparently increases, as you can see in here, then the frequency decreases. On the flip side, observed frequency here is higher than the actual. Wait a sec, please. Actual frequency, and number 2, observed wavelength is higher than the actual wavelengths. Is it clear? Sorry, lower. My bad. Okay, now I'm going to show you something very, very cool. And then we learn about the formula and how to use it. And this is one of the easiest chapters that you'll ever see. Let's see. Okay. Okay. Now see this. Oh no. This is not what I want. I want a GIF actually. Okay. If you look at this whole thing, you might see that as you see at the flip side, like here, you might see that as the dot is moving forward, the wavelength is decreasing, and on the other side, the wavelength is increasing. Do you see? Is it clear?
Yes.
So this is basically called the Doppler's effect. And you might have seen those, when ambulance is coming towards you, the sound is really shrill, and when it goes away from you, sound changes, sort of becomes graver. So that's what Doppler's effect is. So this I wanted to show you that. Now, how do you basically find how the frequency that is changed? The formula is pretty simple. Basically, the actual formula is FO is equal to Fs times V over V plus minus Vs. Okay. Now, interestingly, this formula, you don't need to remember this because it is already given in data page. It's already there. So what you need to remember is that when you see in a question that the source is moving away, you use F naught equals to Fs times V. I'm going to explain what these symbols mean. V plus Vs, you got to add plus. And when it's moving towards an observer, you do F naught equals to Fs times V over V minus Vs. Alright? So you just need to remember that it's positive when the source is moving away and it's negative when the source is moving towards. Okay? Any questions up till now? Now let's write what these are. So F naught is basically observed frequency, the one that the observer is basically receiving. Fs is the frequency of source, that is the actual frequency that the source has. V is the speed of the wave. So whatever wave it is, if it's sound, it's around in air 300 to 350. If it's light, it could be 3.0 times 10 raised to 8. It could be any wave. Vs would be speed of the source. I mean whatever is producing this sound, how fast it is moving. Is it clear, everybody? Any questions? Okay. Now let's try and do one sort of question, and I think you guys will be able to do it. So I'm going to give you this. So it says, warning signal of an ambulance has a frequency of 600 hertz. Now, speed of sound in air is 330 meters per second. The ambulance is traveling with a constant velocity of 25 meters per second towards the observer. Alright, so they have then shown that this is an ambulance that's going, and here's an observer. So this is the initial position, and then the ambulance crosses observer, and that's the final position. So they want you to calculate the change in frequency observed between initial and final positions. Alright, so this is the question. If you have any doubt about the statement or anything, let me know. The formula, I'll just write it for you. F naught equals to Fs times V over V plus minus Vs. So that's the general formula, you already know this. Now I want you to think about it, take like 5 minutes and see if you guys can do this. Alright, you guys got an answer?
Sir, I got negative 91.42.
Negative 91? Why would you? Okay, your answer is correct, but you shouldn't write negative. Because frequency is just a scalar quantity, right? So you always do bigger minus smaller, not final minus initial. Do you understand what I'm saying? Yeah.
Yes.
So initial position has to be F naught equals to Fs times V and V minus Vs because it's moving towards it. So you guys must have gotten like 600 times 330 divided by 330 minus 25, and that would be 649 Hertz, I believe. And the final position, you guys must have Fs times V over V plus Vs. So then 600 times 330 divided by 330 plus 25, and that would be 558 Hertz. So when you're finding the change, right, so the change in frequency would be 649 minus 558, and that should be 91 Hertz. Alright, if you guys have any questions, please let me know. Okay, well, that's good. Now the last thing you're gonna do today is basically something called cathode ray oscilloscope. Now cathode ray oscilloscope is basically used to detect waves or any signals, energy, sort of like that, and displays it as a waveform on the screen. We don't really have to do anything like, let me show you how it is. Like, we don't have to know the working of it, but we gotta know how to find different values through it. So I'm gonna make okay, this wasn't planned. 1 2 3 4 5 6 1 2 3, okay, like that, fine. Now just give me 1 second. I'll just put the markings and then we'll start. So usually it will be given on a grid, of course, because without the grid you won't be able to do this ever. And this is very basic and simple. Okay. Well, that's all right now. So for anything like that, I just want to tell you that on this axis, like there could be a centimeter or something like, or just a division. Like what I mean by this is that this is a division and that is also a division, and it could be centimeter, it could be millimeter, whatever the units are, doesn't really matter. What you need to understand is that on the x-axis you will always you can find the time, and on the y-axis of this you will always find the voltage, and sometimes we say amplitude. Okay, now there are two formulas that you need to remember. First of all, the formula for time period. So to find the time period in a CRO, by the way, this is in a short form, it's called CRO. The time period can be found out by using time base setting multiplied by the length of wave or signal. All right, that's something you need to remember. I'll tell you what time base means. And then you can also find voltage by simply multiplying Y gain setting by the amplitude shown on screen. Okay, like that.
Sarah, what did you write after time period?
Time period is equal to time base setting times length of wave. You write it down, then I'll explain what it means.
Okay.
All right. Done? So basically, you don't have to write the definitions or anything. I just want to explain this to you. That this time base is basically time base. In fact, I'll write setting controls the time shown per unit. Oh no. Okay. So what I'm saying is that basically time base setting controls the time shown per unit division. Like for example, we could say, okay, one division that you see should control like 10 milliseconds. So it means each division will only show 10 milliseconds on the screen. Do you understand? This is like screen settings. And then when you talk about other Y gain setting, so Y gain setting basically is there to basically controls the voltage shown per unit division. So you can actually change this. There's a knob on it, but of course in reality you might use it in your university then. For example, you can set like only 5 volts can be shown on one division. It could be 10, it could be 15, 20, whatever you want. Is it clear?
Yes.
All right, now so suppose here you have like a wave shown. like this, okay? And now they say find the time period and voltage of the wave. All right, so first of all they say time base setting is 10 milliseconds per division and Y gain setting is 5 volts per division, let's suppose. All right, so they've given you this. So what you want to do is, first of all, to find the time period, I'm going to write time period is equal to, the time base setting is 10 milliseconds per division, and now I got to multiply the length of the wave. So how do I find that? I find that I could find this by looking at the crest. If it's a regular wave, like 1, 2, 3, 4, so they're like 4 divisions. I could also from the start to the next start, that's also what I can do. So when I do this, I get 40 milliseconds, which is basically 40 into 10 raised to power minus 3 seconds. Is it clear, everybody?
Yes.
All right. Now, when you want to find the voltage, so you say, okay, the voltage got to be the Y gain setting, which is 5 volts per division. And now you need to find the amplitude. So the thing is that amplitude cannot be found until you know exactly the middle. So this would be the middle of the whole thing. And then the amplitude would be this much, which is basically 2 divisions. So I'm going to multiply 2. So that's going to give me something like 10 volts. So basically the amplitude or the voltage of the wave was 10 volts. Do you get my point now?
Sir, can you repeat?
The voltage one? Aisha?
Yes.
Aisha, we take amplitude from the mean line, right? So if we half the wave off, we have to half it from here, because then there are 2 divisions up, 2 divisions down, you see? You see, Aisha?
Yes.
So this would be the amplitude. The amplitude is like 1 division here and the other one like up here, and this one. So there are 2 divisions in amplitude. That's why I put 2 there. And Y gain setting, which is given as 5 volts. All right?
Yes.
All right. Now, so I guess this would be all for today. We are probably going to finish this chapter tomorrow. And then for the week, I'm going to give you a worksheet. So I hope to see you